How are spin glasses relevant to adiabatic quantum computing? Imagine trying to find the lowest point in a landscape filled with hills and valleys that twist and turn unpredictably. That's what solving a spin glass problem feels like. Spin glasses are materials where tiny magnetic moments, called spins, interact in a disorderly way. These interactions create a very complex energy landscape with many local minima, making it tough to find the true lowest energy state, or ground state. This challenge is similar to solving some of the hardest puzzles in optimization. Adiabatic quantum computing, especially through quantum annealing, uses quantum mechanics to tackle these problems. The idea is to start with a simple system in a known ground state and slowly change it into a more complex one that encodes the problem. If done carefully, the system stays in its lowest energy state throughout the process, ending up with the solution. Spin glasses fit perfectly into this because they're ground states representing solutions to difficult optimization problems. The connection becomes clearer when we look at phase transitions. As the quantum system evolves, it passes through a point where the nature of its state changes sharply. This is called a quantum phase transition. During this transition, the energy gap between the ground state and the next excited state can shrink very quickly. If the gap closes too fast, the system might jump out of the ground state, making the process less efficient. But if the gap closes more slowly, the quantum computer can find the solution faster than classical methods. Quantum spin glasses include quantum fluctuations, which are tiny random changes caused by a magnetic field applied to the system. These fluctuations help the system tunnel through energy barriers, avoiding getting stuck in local minima. Understanding how these fluctuations work is key for designing better quantum annealers, as they control how smoothly the system moves toward the ground state. In real quantum hardware, like the machines made by D-Wave, problems are mapped onto hardware graphs that mimic spin glasses. Embedding these problems onto the hardware can be tricky because of limited connections between qubits. Researchers work on tuning these connections to improve performance, especially near the spin glass phase where the system becomes highly disordered. Simulating quantum spin glasses is another big challenge. Because of their complexity, classical computers struggle to model them accurately. But new methods like quantum Monte Carlo simulations and neural network approaches are helping scientists understand their properties better. This knowledge guides improvements in quantum annealing strategies and helps identify which problems are best suited for quantum solutions. So, in essence, spin glasses are at the heart of adiabatic quantum computing because they representing the kind of tough problems quantum computers are designed to solve. Studying how they behave during phase transitions, how their energy gaps change, and how to embed them into hardware will directly influence how effective quantum annealers can be. This makes spin glasses a fundamental part of the ongoing development of quantum simulation and optimization technologies.